Hi, everyone, and welcome to another workshop in the ICP Zero to Dapp Hackathon. So excited to see all of you guys for another fun one. Today, we are talking about building cross-chain dApps and the very exciting ICP ETH integration. So I'm going to get started straight away by inviting Ben to the stage. Who's just joining us now, and will be able to answer all of your questions and tell you more about this really, really exciting update. Feel free to pop any question that you have in the questions tab. That way it doesn't get lost in the chat, and Ben can see all of them. Also, feel free to use the chat to comment on things, say hi to each other, and stay interactive. Really enjoy it. Hi, Ben.
Hi, hello everyone. Welcome to the Hackathon Encode Club. Today I'll be presenting how to build cross-chain dApps from ICP to EVM chains. So let's get started. Let me give you a brief introduction of how you can build cross-chain dApps from ICP to other EVM chains. ICP is your gateway to all chains, in the sense that we have the unique opportunity for you to make HTTP outcalls. So from within your Canister smart contract. This is not possible on any other chain that I'm aware of, and it's one of the most unique features of the internet computer. So from any on-chain canister, this is the Web3 world in the ICP, and then you can use HTTPS outcalls to call any Web2 service, but also you can call RPC services from Infura, Alchemy, QuickNode. So to any RPC of any EVM chain. And this would allow you to read and write contract data, so interact with other chains. And that offers very exciting and unique opportunities. We have a spectrum of features when we talk about ICP Ethereum integration. I'll just make a brief introduction here. So we have the protocol level integration, which is transaction signing with HTTPS outcalls. This is what we will be looking at today. And with that, we can imagine a whole range of new applications where the core business logic is built on the IC. So IC allows great storage, very powerful computing capabilities. So you can build very complex business logic on the IC, and then value storage can be on any other chain, can be on EVM chain, can be on Bitcoin. Today we'll be focusing on EVM. So this is divided into two phases. Phase one, which is that is done now, and phase two will be rolling out some additional tooling and just some convenience tools for you to makes it easier. And then there's CK tokens. CK tokens is also an important part of our cross-chain integration. CK token stands for, so this is multi-chain tokens that it's chain key, so which I'll explain a bit later. Basically, this is a trustless solution to bring assets from other chains onto the internet computer. We have deployed two examples that are running, which is CKBTC and CKETH. Each of them has some liquidity, a few $1 million. And then this is completely trustless. Everything is governed by a smart contract on the IC. And then using threshold ECDSA, which we'll be explaining a bit later, this will be used as the private key to secure assets on other chains. And then with the CK tokens, we bring other tokens like Ethereum and BTC and other ERC20 tokens onto the IC. And then they can be transacted as IC tokens, which are extremely cheap and fast. So during this inscription craze, people have been using CKETH and CKBTC for inscriptions, millions of transactions per day. We handled it perfectly. So that's a demonstration of what the IC is capable of and the potential of integrating with EVM and other chains. And the third one is EVM compatibility, because IC is very powerful, but still there is a learning curve to building directly on the IC. You need to learn Rust, you need to learn Motoko, one of the two, don't have to learn both. But then there is some barriers. But for existing developers, they might have something developed on Solidity that they would like to port over to the IC. So we have some community efforts running to run a full EVM in an IC canister, and that is possible. So we do offer very unique opportunities. And DFINITY, which is one of our ecosystem projects, is actually offering this. They have the testnet running. They had it running for a while. The mainnet is not live yet, but hopefully it will be live soon. So that's also something to keep an eye on. So key features we'll use and we'll be talking about today are threshold ECDSA and HTTPS outcalls. They are very simple to use, not so simple to develop, but they do offer a lot of very powerful, as you can see. So threshold ECDSA. Threshold ECDSA is a protocol that's part of the ICP's core technology, which is chain key signatures. To put it in simple words, IC nodes are divided into subnets, and each subnet contains a different number of nodes, some 13, some 28. And all the nodes, threshold ECDSA is a way for a subnet to generate a signature, but at the same time, each node is just keeping a very small portion of the private key. So nobody has the private key. Nobody has enough bits to reconstruct the private key. The private key is never reconstructed, but it can be used for signing data. So that's really the particularity of threshold ECDSA. It's developed by the DFINITY team, and we have published some papers about it. If you're interested, you can read about it. So that's really the unique technology that we offer. And because we have this technology, that each canister on the ICP can control a set of ECDSA keys that can be used to generate signatures for any other chain. And wallets can, based on this ECDSA technology, and this would allow a new custodial model, is what we call network custody. So it's not self-custody, because if you do self-custody, you have the possibility of, maybe you lose your key, you lose your, in other words, you can lose your hardware ledger, for example. And with centralized custody, then you have a centralization issue. With this network custody model, there is no party to trust. Of course, you need to trust the network as a whole. So essentially, you trust the blockchain, but you're not trusting any centralized party. You're not trusting any nodes, but you're trusting the network as a whole. And you custody your private key to the network. So this is, it allows a lot of things to be built. And using threshold ECDSA is very simple, although the technology is very complex. We have abstracted it and made it very simple to use. So the feature can be used by issuing inter-canister calls to the management canister. And the endpoints we'll be looking at are just sign with ECDSA and ECDSA public key. I will probably share the link in the chat, so you can also take a look. So the document that we'll be looking at is the Internet Computer Interface Specification. It's a very long document. It's not easy to digest, but it's the reference document if you want to develop anything on the internet computer. So as you can see, we have a long list of features of the blockchain itself. And the methods we're interested in are, we can go through these quickly. So you create canister, you can install code. So all the canister related operations are calls to the management canister. You can generate true random numbers, and then you can do ECDSA and HTTPS. So these are the things we'll be looking at. And then there are also Bitcoin related endpoints from the Bitcoin canister. So you can Bitcoin get UTXOs, query, get balance, send transaction, and so on. So if you're interested, you can take a look at this document. The methods we'll be using are ECDSA public key. And this would give you, so each canister, you can define the derivation path of a public key. So you have one key that you can use, but you can also specify a derivation path so you can use multiple public keys within public-private key pairs within one canister. And this would really give you the flexibility of, for example, controlling multiple accounts or even one account per user, one Ethereum address per user, and things like that. And then the keys are only usable by your canister. So these are linked to the canister IDs. Another canister can call the same derivation path, but the root path is derived to your canister endpoint. So nobody can, from another canister, can use your private keys. And then the second one is just sign with ECDSA. You sign a hash. It will be signed using the key. And then you can use a signature for your Ethereum transactions. So far, do you have any questions?
There were some questions in the chat. I don't know if you would like me to read them out to you. I can, or if it's easier for you to look at them yourself.
Yes. So first question, Morris mentioned ECDSA was in the works too. So it is being worked on. We do not have a concrete timestamp that we can share with you. Is likely to be Q2, Q3 this year, but there's no official timestamp that has been, that we can promise. So it is being worked on. That's what I can confirm. So ECDSA Schnorr signatures. Another question: any reason why ICP has no testnet? So first of all, to test, what you can do is you can go to our Discord and you can ask for some cycles. So ICP itself, how we structure is a little bit different than most of other blockchains. So the native currency of the network is cycles, and cycles is what you would use to pay for your transaction, pay for storage, pay for computing. The user does not need to pay; it's the canister who pays, and that is, in our model, is the canister pays for everything, just like any Web2 dApp, right? If I develop a dApp and I put it on AWS, I will be responsible for paying everything, and then I get revenue from users, and then they can pay in some other currency, and then I can deal with the, running all the servers and infrastructure. ICP has adopted a similar mindset or approach. So cycles is the native currency. It's tied to the US dollar. It's stable. Even if ICP price rises or falls, how much you pay for storage or computing does not change, which makes sense. And the reason that ICP has no testnet is, first of all, we have this faucet where you can get some cycles to play with, and then it's expensive to set up a testnet, and the state is not So we don't see a clear benefit of using the testnet. That's why we just advise developers either to test in the local environment, that is also possible, but otherwise just test on the mainnet, because you will be likely interacting with some other smart contracts already deployed with other canisters. And that is impossible to replicate in the testnet or in the local environment. So we just recommend developers to test on the mainnet. You want verifiable testing results. I'm not exactly sure I understand this question. Maybe you can elaborate a bit more. So ICP does not have a true blockchain explorer. We have an explorer for transactions. We have an explorer for, if you go to dashboard.internet.org, you will see explorer for different metrics. But blocks on the IC are by default not public. This is a conscious decision that we have made. So you cannot verify a data. It's by default public, unless the canister wants to publish it. And then the canister can decide to publish whatever data. So for example, all ICRC tokens, those are deployed in canisters, and they decided to publish token transfer, minting, so these kinds of data. So if you go to dashboard.internet.org, you can see all of these transactions, but that is a conscious decision from the canister to publish those data. So for verifiable testing, I'm not sure exactly what verifiable means, but usually what we do is we set up a test suite and we execute, and then we just verify the result by querying some target canister to ensure that it has entered a certain state. If you want more advanced testing, there is a tool called IC State Machine tests. I'm not sure exactly where to find it. If you go in DFINITY GitHub and search state machine tests, I'm sure you'll find it. But it's not very friendly for newcomers, let's say. I thought CKUSDC is still in the works. Yes, that is correct. Not only USDC, all ERC20 tokens are in the works. How safe is it against canister runners to agree to steal CKBTC? So I assume by canister runners you mean the controller of the canister. So the controller of the canister, by upgrading the dApp, can theoretically use the ECDSA private key for other reasons. So for example, to transfer BTC out. But CKBTC is under control of the NNS, if I'm not mistaken. So NNS is the governance framework for the entire network, not only CKBTC, but also how nodes are configured. So the network architecture and the code aspects of the IC. So it's and that's the voting is by staking ICP, right? So right now there is, I don't know how many millions, hundreds of millions of ICP staked, and that's the security guarantee. How to black hole a canister? There is a black hole. Let me see if I can find the link quickly. There's a black hole canister. That's also in the, I'll share two links. I'll just put it in the chat. So there's an article on trusting canisters. And then the second link is an implementation of the black hole canister. Okay. Can you call a canister to call another canister? Yes, you can. the blockchain is completely asynchronous, so you can send intercanister calls as you wish, but they won't be executed atomically. They won't be executed in the same block. There is, depending on whether it's within the same subnet or across subnets, there can be a delay of a couple of seconds up to maybe 10 seconds if you're making a round trip, or even more than 10 seconds, depending. Composite queries for CKE, that's a very big topic. Let me skip that one. Okay, let's quickly continue. So that's about threshold ECDSA. Thank you for the question. That were great questions. So HTTPS outcalls is another feature on the IC that allows canisters to call any HTTPS endpoint on the internet. And by calling RPCs, you can interact with other chains. There are several caveats to using HTTPS outcalls. So it's called by calling the management canister using HTTP request. There's several things you need to consider when making HTTPS outcalls. So first of all nodes of a subnet would make the same call to that endpoint. So for example, if you have an Ethereum key that is rate limited, and you are in the 13-node subnet, you make an HTTP outcall to your Infura using your private key, then like it would actually make 13 calls to the same query. And then each node would individually, because this is pre-consensus, each node would individually get a response from the API endpoint. And then there is a consensus to be run. And all of them have to have the same response. Well, not all of them, the 2/3 needs to have the same in order to reach consensus. So that is a limitation of HTTPS outcalls. That means the endpoint call should be idempotent, which means for query calls, it doesn't matter. But for example, for updates, so for post, then the service must be built in a way that when multiple calls with the same data arrive, they should be treated as one call. So for example, if I have an API endpoint which is increment, it should not be implemented in a way that each time I receive the increment message, I increment by 1. It should have some additional fields, for example, announce. And so if 13 calls come at the same time or within a couple of seconds difference, I receive them, I'll treat them as one call. So that's a very important point when you are building an API endpoint to be called via the internet computer. But if you do not build the API endpoint, you're using third-party endpoint, then you need to choose accordingly which endpoints you call. Sometimes it's not possible to ensure that they all receive the exact same response because some data might differ, some headers might differ, for example. And then that's why we have the transform function that's also written in the in this interface specification. So if you look at here, IC method HTTP requests, if you scroll down, you will see there is a transform function. So the transform function will be applied to the raw responses before they go through consensus. So that's one way if you're receiving different responses, but it's just some non-vital metadata or headers that differ. You can still get a valid response. You can still get the true data that you're looking for to go through consensus. And then there is another important thing to set is max response bias. This is optional, but in reality, you should almost always set it because it specifies the maximal size of response in bytes. However, how much you pay is directly linked to the max response bytes. So if you do not specify any value, it's assumed 2 megabytes. In reality, there is rarely a case where a response is 2 megabytes. So you need to experiment and set a smaller value, 5K, 10 kilobytes, and you will pay accordingly. Otherwise, you will have a max response bytes of 2 megabytes, and you will pay for it. So that will be, I forgot the cost. So the cost of doing public key is virtually free, I believe. And then sign with ECDSA, you will be paying, I'm not sure of the exact current cost. I think it's a few dollar cents per signature. So do keep that in mind. And the HTTPS Outcalls is very cheap. You pay less than 1 cent for most of the cases. If it's 2 megabytes, I think you pay around 1 or 2 cents. I could be wrong. You should try how many cycles it charges you. So that's how you use HTTPS Outcalls. The transform function, and keep in mind that is IPv6 only. If you have an IPv4 only endpoint, then it would not be reachable because Internet Computer nodes use IPv6. Okay, let's see if we have questions. What is the use of SNS and NNS? So NNS is the governance of the entire network, and SNS is the governance of DAOs. So you can say, I want to create an SNS by proposing to the NNS, and then if the NNS voted yes, then an SNS will be created, and it will be a DAO. And you can propose to the SNS for matters that governance matters of your DAO, including code upgrades and non-code topics. Is there a way you can call canister between as or Rust to a Bitfinity dApp? That I'm not sure. I'm not sure. You should check with Bitfinity. Ethereum, the big push on contract security and tons of data, unknown exploits. Known exploits on the IC. So Ethereum has a longer history, right? We have a shorter history, so we haven't formulated that. So there are several issues that you should pay attention to. So there is no notion of re-entrancy on the IC since it's not atomic. So it's asynchronous. But then there are issues related to this asynchronicity that you need to manage. So for example, when you make from your smart contract calls to other canisters, if the other canisters don't reply, they can delay response by making other calls, by making further calls to other canisters. And if they do it continuously, then you are blocked from making upgrades. So you can no longer upgrade your canister. This is something that we are working on a fix. It's more complicated. It's linked to execution and open call context and stuff like that. But there is some work underway to fix this vulnerability. Sorry. So this is why you see, for example, DEX is on the IC. You can't just add any token pair that you create, because a DEX would be making calls to other to the token canisters. And if the token canister they don't know, they don't trust, it can mess up their DEX canister. That's why, yeah, you can't just add any liquidity pair. This is a known issue and it's been fixed. But otherwise, no exploits in smart contracts. Developers do mess up executing scripts, for example. If you do it the wrong way, you might lose controllership to your canister. You might, yeah. But there's no like big exploit yet on the IC. Could an endpoint block traffic if it receives a lot of requests? So yes, if all nodes in the subnet do request an endpoint, it might see this as a DDoS. Well, subnets are relatively small in the scale of the Web 2 internet. So it's 13 nodes, 28 nodes. The NNS subnet is the biggest, like 40 nodes or something like that. So it's not a huge number of requests in Web 2 terms. What's the price for Outcalls right now? 2 megabytes. You need to check. Do you have any resources? Yes, I have some links that I'll be sharing. I made HTTP Outcalls in main and return connect to URL. So you need to see if it does not connect to URL. You need to see if it supports IPv6. That's an important point. Is there any way to encrypt API key when making outcalls? So when you make an outcall, it's typically not encrypted in the. I mean, the transport layer is already not encrypted. I mean, it's encrypted HTTPS, but it's not otherwise encrypted. So I don't know exactly what you mean by encrypt the key. What are software lifecycle SLCD process? Those are very broad architectural questions. How do you design a microservice architecture? Those are very broad architectural questions. So yeah, I would urge you to explore a bit more, look at some example applications built on the IC, and you would hope you'll get a better idea. I think we can skip this Ethereum JSON RPC. It's just you will be making this JSON HTTP call, for example, ETH call, and then with you can send this to any endpoint, and then you can get a response. So we have built a convenience feature, which is an Ethereum RPC canister. So instead of you having to manage the, well, basically everything, so using the raw HTTPS outcalls, you can make an intercanister call to the Ethereum RPC canister. And then this RPC canister would in turn make the HTTPS outcalls to the nodes. It does simplify development a little bit, as we will see. So if we put all we have talked about together, to build a cross-chain dApp on the IC, you develop your code in the canister. You use threshold ECDSA for signing, and then you would basically call the EVM RPC canister with your JSON data, and then this RPC canister would manage this HTTPS interface, so calling out to other EVMs, and then getting the response and returning the response to you. So I will share a few links. first of all, the EVM canister, since we talked about it. So this is the code for the EVM canister that we talked about. You don't have to read and understand it, but if you want to understand how HTTPS works, that would be a good example. Then I have a few other examples. We have built a wallet, which is called the Oisy wallet. So this is a wallet that uses so the wallet is in the canister, and it uses threshold ECDSA to sign Ethereum transactions, and then you can execute those transactions. So I'll probably show you a demo. It's really straightforward. And then another is ERC20 ICP. So we built a we brought ICP token to on Ethereum as an ERC20 token. So the code is here. And it also uses ECDSA, threshold ECDSA to generate signatures, and the EVM RPC canister to write data to Ethereum. I think it reads, it doesn't write. Yeah, to read data from Ethereum. So it would monitor Ethereum events. And yeah, so these are very good resources. I suggest you take a look at, especially the last two, the Oisy wallet and the ERC20 ICP. The codes of these two are relatively simple. You can quickly go through them, and then they will be very helpful. Let me maybe quickly show you the Oisy if you haven't seen already. I'm sure many of you have seen. So we built a wallet that's running completely on the IC. So you authorize through internet identity. I just connected. And then it would initialize wallet, so securing session with internet identity, and then retrieving your Ethereum public key. So this is a call to the get public key endpoint of the management canister that we just looked at. And then a private key is stored within this subnet, like spread across all nodes of the subnet. And then you can hold Ethereum assets. You can hold Ethereum, you can hold ICP token on Ethereum, which is ERC20 ICP I just shared. It's an ERC20 tokens. And then a range of other tokens. You can add new token. You can connect via Wallet Connect, and then you can send and receive funds. I don't have any funds here, but you can play with it. This is just, I wanted to show, because I wanted to show you a demo of what is possible with threshold ECDSA and Ethereum RPC outcalls. You can imagine this to be not only Ethereum, but 30 other chains, just by calling different RPC. And the key is secure. There is no security risk. So, okay, that's a very quick one. So there is a quick starter app. I would also share the link in the chat. You can also scan the code. Yeah, I'll share a link in the chat. It's easier. So this is an IC Ethereum starter project that I have made. It uses Rust. If you use Motoko, there is a similar starter project that's using Motoko under the DFINITY repo. But I wanted to quickly go through this one with you. So if you're starting building an Ethereum integration, you can consider referencing this one. How to use is very simple. Clone, install the toolchain, just run through. Build, there it just tells you, and then you run these scripts for some initial settings, and then you will be able to run. Let's go through the code quickly. because I think we still have some time. So you don't need to worry about most of them. Let's look at the main functionality from main.rs. So those are boilerplate code. What it does is you have sign requests, and you can use this to sign a legacy transaction, which is a non-EIP 1559 transaction. And then you can use sign request EIP 1559 to sign 1559 transactions. So just a note of how you use this function. I have made it very simple because I wanted to demonstrate different functionalities separately so that you don't have to mix them up. You can mix them up. So this one returns a string. The string is a hex encoding of your signature, and you can just get the signature, and so you can this is an owner only function. So you can read the signature, and then you can send it on chain to be executed, for example. I have tried, it works. And then you can do personal sign, which is the same as, for example, when you log in Uniswap, you have a personal sign to say, I'm logging in to Uniswap, I agree with the terms and conditions. So that's a personal sign signs a string, and you get a signature also in the string. You can also sign an arbitrary hash, so you can sign a hash of a message. So these are demonstration of the Ethereum signing functionalities. Maybe let's look at personal sign in a bit more detail. So the config just, I'm not sure what it does. Oh yeah, ECDSA has a key name, so that's just a static string that's used as part of the derivation path. You don't need to worry about it. You can set it to key 1, for example. And then it would just get those bytes and use Ethereum signed message. It would concatenate this with the length and with the bytes itself. That's how you do a personal sign message. And then you calculate the hash, and then you get a public key and a signature. We are calling the pub key and signature function, which is in TCDSA.rs. So if you look at this one, the TCDSA.rs uses the management calls that we've been talking about. You can get the public key of, so you are just calling ECDSA public key. So this ECDSA public key is an imported, is how you call the management canister, is ICCDK API, management canister, ECDSA public key, and sign with ECDSA. So these are the two functions you can call. And here we called ECDSA public key with a request, and we await the response, which gives you a call result. And the same thing goes for signature, so that's very easy. And pub key and signature just does the two at the same time using futures.join. So it's very straightforward, and I hope it's easy to understand. So let's go back to the personal sign. Sorry. So yeah, you get public key and signature. The second parameter, the empty vector, is a derivation path. So we are just managing one address. So we use an empty derivation path. But if you have multiple users, for example, if you want each user to have a separate wallet, all controlled from within the same canister, then you can use the user's principal encoded as part of the derivation path. And then ECDSA signature from prehash to string compact. It's just some helper functions and utilities you can. Everything is within this repo you can check. And then, so these are the ECDSA related functionalities. And then there is RPC, so ETH RPC call. As you can see, it's call canister call with payment. Payment is payment in cycles, so you attach some cycles to the call. And then you're calling the ETH RPC canister, so you're not directly calling the management canister because we are using the RPC canister as a convenience feature. And then you attach the JSON. And the max response bytes is a configuration. So if you don't set it, it's also fine. You will just pay for 2 megabytes. And then, so for example, here is an example, right? It gets Vitalik's wallet balance. You just query that canister with method ETH get balance with Vitalik's wallet address latest, and then make the ETH RPC call. And then the result, you just need to parse the result, which is very straightforward. And you'll be getting the balance of Vitalik. And below we have a demo where we monitor events of an Ethereum contract. So there's a sample ERC20 address. You can put in any ERC20 contract that you would like to monitor. And then it uses ETH get logs to get the events. And then it would match certain event IDs. Process logs that matches the event IDs. So for example, when we monitor burn events, then it would just match event IDs. If it matches burn event, then it would record. So this is the actual code that's used in the ERC20 ICP. And then event logs are synced. So how you log events, this is a bit long code, but all it does is it parses events and logs them. That's all what it does. And then the periodic task, that's also an interesting feature because within an ICP, so for example, on Ethereum, if you want to trigger a smart contract, you have to send a transaction. And if you want to periodically trigger it, you have to send multiple transactions. You need to configure an external service to send one transaction to the Ethereum chain, say, every 10 minutes. On the IC, there is a feature to be used that's called the timer. So once you set up the timer, it would periodically call. You can set it with a delay. So if there is something within the canister that you would like to get executed once every 10 minutes, 15 minutes, or even 10 seconds, you can just set up a timer. And each time it executes, because the canister pays for its own cycles. So each time it executes, the canister pays for the cycles, but then you don't need to configure any external service to trigger this task, which is very nice. And so if you want to try it yourself, you can just clone this repo and set it up with these configuration parameters. And you should be able to try all of the endpoints that I have explained. Periodic task isn't pub, yeah, because it's called, it doesn't need to be. Can you compare heartbeat and timers? Yeah, so heartbeat, I think it makes more sense to use timers now. Heartbeat is just one, it's executed every block. There could be use cases for it, but yeah, for most use cases, I would suggest using a timer because it offers more flexibility. you can just set longer intervals. For example, if you're monitoring Ethereum blocks, you don't need to execute every block because Ethereum block time is 12 seconds. So you can set it to monitor every 12 seconds or 6 seconds if you want. Motoko is for end user devs, and building infra has one option, Rust. Well, there are use cases for both of them. I'm a Rust user. I think if you're building some simple applications, Motoko would work. But Rust has more. The problem with Motoko is you can't use existing libraries, right? So since it's a new language, you have to build all the libraries, or it has already been built by either DFINITY or someone from the community. What's good about Rust is you can use existing libraries, because for the IC, the execution engine is WASM, and there are many libraries you can use that is already built. So for example, let's again take a look at the ETH startup project. If we go into cargo.toml, you will see we are using something called ETH ABI and ETH core and ETH num for numbers. And then not to mention futures and other stuff, right? K256, which is a crypto library, which on Motoko somebody needs to build it. So if we look at one of the functions that we did take a look at previously, the EIP 1559 transaction. We are using ETH core type transaction, EIP 1559 transaction requests, and signature. And it's just already built. There's much less code you need to write. You do need to know Rust libraries. So if you're not a Rust developer, you might find yourself in a position where you're at the same time learning Rust itself and also learning the internet computer. That can be confusing and difficult at times. But it's not that complicated. And so, for example, RLP signed, that's something that's used right now in REVM, for example, and we just reuse it. So we actually write a lot less code using these existing libraries. Okay, next question. Has anyone tried to create a personal club server? I think there's a project. I haven't been following this project. There's a project called ICP. They are building something. Otherwise, I can show you. There is a meme project. That's a meme project on the IC. Windows 98. And then, okay, you can have the beloved Clippy. And then dApps, for example, those are real dApps built on the IC. You can open up ICP swap. I don't know how they built it. It's just the front end. It's I think they just iframe with a very nice style. So that's swap DEX. And then you can use OpenChat. But it refused to connect. You can do pinball. So yeah, I'm sure people build all kinds of things, and hope you can find something to build on the IC too. Is there for Coinbase, right? The ICP, my code base here. Right, that's a very good question. So the question is there a way to encrypt the third-party API key within the canister? So not when making the outcall, but within the canister, because otherwise nodes can theoretically see your private key. There is no way to do that right now. We are working on a threshold encryption feature, but that would require some research. So it won't be, don't expect it in the next 6 to 9 months. Yeah, but we're working on the threshold encryption feature. So a threshold encryption feature is similar to threshold signing, but you don't do signing, you do encryption. And every node has a share of the private key. Nobody has a private key. You don't need to reconstruct the private key. You can just encrypt and decrypt. And that's a really nice feature. But it's not possible today. So your API key would be plain text and accessible to nodes. But it's a reasonable risk. So you do assume some risk, but you maybe rotate the key and use some other ways to mitigate this. Okay. All right. I think that's all the questions.
Yeah, thank you so much, Ben. Really interesting stuff. I really enjoyed it, and it seems like everyone else did as well. A lot of questions come through, so thank you for going through all of those as well. And yeah, for all of you guys watching, if you have any more questions or anything else pops up, feel free to post it in the Encode Club dedicated hackathon server or channel, on the Encode Club server. I'm also going to send the link to the ICP developer community Discord server, where I know that there's lots and lots of great support. They also run office hours every Wednesday, so it could be a good idea to check that out next Wednesday and just kind of chat more to people from DFINITY. Do you have any final words of encouragement, Ben, before we log off?
Well, thank you all for participating. Thank you for the great questions. I just hope you a lot of fun developing on the IC.
Thank you. Okay. Yeah, have fun, everyone, and I'll see you guys very soon.